Graduate statistics and mathematics at the University of California. She's spent several years in research, mostly medical statistics and analysis. She presented a paper on a new physical theory at the International Tesla Symposium in 1988, so this talk will be somewhat of an extension of that. She now heads an independent research project based on this new physical theory. So let's welcome Shelly Thompson. Just, I guess we'll do that side. Ooh. There.
All right. We in business?
We're in business.
Okay. Thank you all for coming to hear me so early in the morning. I really appreciate it. It's a great privilege to be invited here. There are very few forums where genuinely new ideas in science can be proposed and listened to. In 1988, I presented a paper on the physical theory that I thought of. It was an abstract paper. It took a full hour to do this, and I'm going to have to recap it for you as quickly as possible. I'm going to have to hurry through that part so that we'll have time to discuss the experiments that my group did in the ensuing 2 years. There won't be a quiz, and there won't be any equations. Could we have the lights down so we can start on the slides? All right. Okay, the theory concerns the propagation of change, and it begins with the idea that the world is real. It is composed of objects about which we can make meaningful observations. Now, what's an object? Any object we can refer to has a history. It has a unique past. It has a unique collection of possible events in which it could have figured. It has a unique collection of events in which it might figure at some time in the future. Sorry about this.
We got it.
All right, this is our definition. An object includes all of its past, present, future, and possible interactions. Any interaction alters both the object and the observer. The observer is an object in the system, too. It might be helpful to think of the object as a seed contained in a shell or envelope of possible events. By an event, I mean an interaction with another object. The events in which an object might be involved or has been involved will be referred to pretty much interchangeably as its possible states or available states. Now, the observer is an object in this theory. Therefore, there is no passive act of observation. Any observation creates change in both observer and observed, no matter how it is accomplished. If I were to borrow some ideas from conventional physics, I would say that the state vector might be considered roughly equivalent to an object's collection of possible states. From the standpoint of this theory, the state vector never collapses. We continually inhabit a complex present in which everything that can happen does. All possibilities coincide in the now. For this reason, we say that objects are not time-wise separable. There is no intrinsic time-wise order in the collection of possible states. It follows that there is no intrinsic space-wise order in that collection either. Now, this idea of objects allows us to develop a definition of realness. What good is a physical theory if you can't unambiguously decide what's real? Well, given an object, you have an object surrounded by its collection of possible states, past, present, future, possible interactions in which it might be involved. If you take that collection and remove the object, what you have left is the unique whole, the unique space in the universe of relationships which that object occupies. That is called the null space of the object. It's unique to the object, and by definition, every real thing has a null space. Now we can start to talk about change. Change is a process that happens to real things. We're not used to thinking of change as a force, but you can think of it this way. And the undifferentiated force of change, the raw force of change, is called effect. And the process of manifestation of effect is called event generation. Now suppose we decided to represent the available states of objects in matrix form, just as a mathematical notation. Then you would think of an object as an aggregate of matrices. Event generation, the occurrence of change, could be represented as transformations that alter those matrix entries. Now, you can then see the event generation transformations can be ordered in terms of how many independent components they must contain in order to account for a particular matrix change. So while you can't actually know the matrix entries, the individual entries, you can say something about the event generation transformations. They have a property called relevant dimensionality, which is associated with the number of independent components they have to produce a particular transformation. Now, we can proceed to define a property called resonance. In the collection of matrices representing the available states of the object, we say that two matrices are resonant if they have the same relevant dimensionality and if they're isomorphic. That's a fairly stringent condition. And we may not have to be that strict with it eventually. But if they're isomorphic and they have the same relevant dimensionality, they certainly are resonant. It's a mathematical term. Essentially, there's a one-to-one, there's a linear mapping possible between the two. All right, now, we arrive at the thought that suppose the two matrices have the same relevant dimensionality, but they're actually not isomorphic. If they have the same relevant dimensionality, they are images. If they have the same relevant dimensionality and they are not isomorphic, they are inverse images. We're going to talk about images later on, which is why I felt that you should see this. The nice thing about viewing event generation as composed of different transformations in this way is that it's possible, at least in theory, to make alterations. It is possible to create change which has a shape or characteristic. It's possible to alter the collection of possible states of an object, and this collection figures, in theory, very prominently in the later behavior of the object, and I'm talking about its physical properties.
What does RD stand for?
Relevant dimensionality. Now, when we're considering how change happens in a situation like this, we'd say that a given propagation event would be noticed at different times by different observers, because change is not uniform. Remember that an observer consists of a large collection of matrices, and effect propagates immediately between resonant matrices. and it tends to die out, to be attenuated between non-resonant matrices. Since this is true, the change in an object cannot be uniform. So that when we have a given propagation event, while in theory the propagation event itself is instantaneous, it's the only true concept of simultaneity the theory contains, two observers would notice it at different times because the observers are probably not mutually resonant. There would be no point in adding up the observers' times and constructing some sort of average to find out when the event really occurred, because in theory it really did occur at different times for the observers. Now, the production of time-wise anomalies is an important aspect of the theory. Essentially, it says that no propagation event of any significance can take place without producing any time-wise anomalies. It is the unique signature of that pulse or that propagation event. If we wanted to assign relative magnitude to the event generation event, we would simply say that you can compare in terms of the relative size of the time-wise anomalies created. Now, looked at in this way, we'd have to say that non-local or superluminal connections between events are the rule rather than the exception. We don't always see the sudden, the synchronicitous propagation of change, because the collection of possible states in the objects around us are not ordered. They're homogenized, disorderly, non-aligned. In principle, though, the propagation is instantaneous. Now, if we were going to develop this idea mathematically, we could assert the objects as points in a topological space, and relevant dimensionality is the metric. Connectivity between objects is a property of their mutually resonant matrices, and it's synchronistic rather than time-wise or space-wise. We managed to construct the entire theory without any reference, without having to depend on established concepts in physics like waves, particles, and fields. Which means that somehow, if this theory is really pertinent to reality, it has to account for field effects. And the way I think you would have to do it is this. You would have to look at field effects not so much as propagation of whatever is creating the field, not so much as propagation, but as attenuation. From this standpoint, the remarkable thing is not that electric current flows along the wire, but that it doesn't flow everywhere else. This doesn't conflict with the way these things are usually handled. It's simply a new way of looking at it, somewhat different way of looking at it. Now, I think we're through with the slides. Could we have the lights back on? Now I can see my notes. Thank you. All right, these ideas are helpful from a technological standpoint. As I said, we can't know what the matrix entries are, and in any case, the act of knowing would change them. But we can know something about relevant dimensionality. In particular, we can determine it by experiment. And that's the hinge of the matter. If relevant dimensionality turns out to be a small finite number, this theory immediately yields important practical developments. I think it will turn out to be a small number, or at least a practical number, if for no other reason than you can, in principle, enforce a resonance artificially. But that remains to be seen. It's the general suggestion in this theory that the process of event generation itself is technologically accessible. This is the equivalent problem to tapping the zero-point energy or the vacuum fluctuation. It's simply approached very differently. Now, there are various possible technological consequences to this that make it interesting to do. It makes it worth finding out whether this is true. There's some very interesting consequences for an approach to artificial intelligence. Suppose you could build a system which could discriminate between possible states. I don't see why not. It would seem to be practical even right now. Such a system would not require a computer interface. It would not require the immense mass of programming and data we normally put into a computerized artificial intelligence mode. And it would perform some activities that computers can't really do. To me, however, the most interesting aspect of this theory, the primary product of this theory, lies in the idea of motion. According to the theory, recalling how objects are defined, the location of an object is an observer-related phenomenon. In other words, the difference between the object here and the object elsewhere is describable in terms of its available states. In theory, we can apply event generation transformations to an object to annihilate or collapse the matrices associated with selected object states. The energy requirements for this process refer to the resonance character of the matrices. This means, in theory, we can force an object to make transit between its possible states, and it may turn out to be an energy-efficient process. Now, with regard to motion, it follows that it's theoretically possible to collapse or delete the matrices associated with the object's presence at point A, empower or resonate the matrices associated with the object at point B, and literally pump the object from point A to point B. It does not go through the intervening space. In a sense, it never really goes anywhere. It already is every place it has been or could be. The energy requirements for this process have nothing to do with the geographical distance between point A and point B. They have nothing directly to do with the size of the object, only with the resonance character of the object. All right, so starting from a simple premise that objects have histories and that they keep on having histories, these remarkable possibilities suddenly materialized. What does it mean to an experimenter? Well, there are some substantial differences between this theory and standard approaches which you have to take into account. The significant fact is that the possible states of an object are pooled. There is no intrinsic order in the available states except with regard to resonance. As experimenters, we immediately confront what I think of as the on-off switch problem. When we turn on the electric lights, we flip a switch that closes a circuit that supplies power to the light. As soon as the switch is turned on becomes, being lit becomes a part of the system's collection of available states. It's arguable that it happens before then, but it certainly does happen at that point. When you turn the switch off, that available state, the on state, doesn't disappear from the collection of available states. It's still there. So if you're attempting to supply power to the system using an event generation process, you need an entirely different theory of control. And this is where we started. In theory, it's not difficult to generate the pulse. Controlling it is another matter entirely. And we spent a lot of time thinking about the on-off switch issue. What I'm going to present to you is an experiment within an experiment. And two general ideas went into it. First, in order to get propagation events by actions addressed to the system, we need to establish a powerful condition of mutual resonance between the system components. We have to somehow make all the parts of the system mutually resonant so that effect will propagate in them. This is done by controlling the possible states of the components, in other words, by dedication conditions. And I'll have a lot more to say about that in a minute. The second thing we decided to do was to power up the system, to increase its collection, to increase the power in the system by increasing its collection of possible states, adding possible states. Now, to dedicate a system, you have to control the collection of possible states. And what that means is, if your system contains a light that's due to be lit as part of your experiment and part of your protocol, you must make sure that it is not lit at any other time for any other purpose. And this is harder to do than you may think, because many people assume that the future states of the experiment, including the future states of the experimental apparatus, most people assume that these can't have any effect on the present. In this theory, it's all here right now. Therefore, you have to use your equipment, your experimental apparatus, consistent with the protocol at all times, including when the experiment is not running, because there is no way to separate the before and after states of the experiment. Now, it's a lot of trouble to do this. It's quite hard to build one of these systems because you have to remember to do things and not do things in a very unusual pattern. Most experimenters never dedicate a system because they think the future cannot affect the past. They don't control the possible states of their system. The powerful synchronistic phenomena predicted in this theory, in a system which is not dedicated, which is not controlled, the synchronistic phenomena predicted in this theory are most likely to emerge at the very start of the experiment, especially if it's an important experiment with a lot of possible states riding on it, and then they disappear. Now, typically, when experimenters encounter this phenomenon, typically these early anomalous data go right in the trash can. They don't understand why it happens, it's not repeatable, and they continue to run their equipment until the different components of the system attain a mutual resonance, which is normally a low-grade resonance where you don't get this kind of synchronistic propagation. At least that's what I think is happening. Now let's see, I need some help with this item here. Not on top of that's the transparency there. Okay. Now, we also need the overhead projector plugged in. It means we'll have to unplug the slide projector. Right, and that first thing right on top. Now, the general purpose of this can everybody see the bottom? Not too well, huh? All right. Well, that's the best we can do. Okay, and I will explain this to you. Now, our basic problem as experimenters is this. I want to do propagation studies. And in order to study the propagation of something, you have to turn it off and on. You have to be able to control the pulse. It has to happen when you want it to happen, one way or another. And this experiment incorporates our initial best guess at how to deal with the on-off switch problem. At the top, I should say that everything, see San Francisco there about the upper middle of the page? Everything above there is in North Carolina. And this part of the system was built by Ross Dunseith, my co-researcher and engineer. At the very top you see something marked force detector array. This is what we hoped would be the movable part of our on-off switch. And it consists of 4 piezoelectric Bender elements. These little elements are quite small. They're only about a centimeter square. And you would never see them even if you looked at the box they're in, because they're covered in conductive paint and silicone rubber and embedded in a system. There are 4 of these things mounted inside a steel box, residing on a vibration isolation table in a Faraday cage shielded room. The electrical signals are preamplified inside the steel box and sent by cable to a chart recorder and microcomputers located outside the room. Let's see now, this is computer, there's the chart recorder right under the force detector array. There's computer number 1, computer number 2. Now computer number 2 is connected by a modem to computer number 3. Everything from this point down is in California. This is the operator end of the system. It's quite portable. We could set it up anywhere. Now, there's a modem. Computer number 3 operates a number of pieces of equipment. It operates a control box, which is attached to some lights and bells. It operates a light display. That's a new piece of equipment. We didn't have it in September of '88 when the incident happened that I want to discuss with you in detail. We have a monitor, an operator's keyboard, and a programmer's keyboard. Now, the operator's keyboard is a very special device. It can send only 5 different keys, only those. The programmer's keyboard is a fully operational, regular, extended keyboard. We need that to work with the system. Between these, there's a manual toggle switch. Only one of these keyboards can be live at a time. These things, the monitor and the operator's keyboard, are in an experimental enclosure. Okay, now recall that the power for a propagation event comes from the possible states of the elements of the system, specifically from the resonance or coherence of the possible states. Now, what happened to our... Oh, okay. Okay. The most stringently dedicated elements in this system are the force detector array. This is not used in any other experiments. No one is allowed to fool with it, handle it, look at it. No one even knows where it is. And the operator's keyboard, which is only used during experiments, not for any other purpose. It's not put on public display, it's not photographed, we don't allow the general public to fiddle with the buttons, and I don't allow my technicians to do that either. We have tried, within the constraints of very limited resources, we have tried to obtain control, to keep control of the possible states of all of this equipment. And our best success has been with the force detector array and the operator's keyboard. Theoretically, this should be enough, because what we're looking for is synchronistic propagation, synchronistic events. What we want is for some person to push a key on the operator's keyboard and an array event to occur. Now let me describe an array event for you. As you probably know, these crystals are live. They have behavior. They're emitting small signals all the time for whatever reasons. We use a 2-threshold system. We don't want this system, we don't want this switch to go off for random reasons or its own reasons or environmental reasons. Our artifact controls are as good as we can possibly make them. There are 4 elements in this array, and we use a 2-threshold system. There's a high threshold and a low threshold. Now the signals are sampled at 1,000 hertz, and the experiment works like this. Well, with the artifact control, an array event is declared if and only if one of the sensors is above high threshold, while the other 3 are below low threshold for 5 continuous samples. That's a fairly strict criteria. The event is declared to end when either the one sensor drops below high threshold or any one of the others comes up above low threshold. With this, we anticipated that artifactual activation of the system would be quite rare, and that has been the case. Now, so you know about the dedication, you know about the artifact control. I remind you of our original issue. We needed to add effect to the system. We want to force events to propagate in this system, and the way to do it is to add possible states. We could have done this by adding complex equipment, attaching complex equipment to the system, especially equipment which has a very diverse inventory of possible states. However, we had a much more convenient and much less expensive solution, we decided to add operators. What we did was to see, a human being is a walking inventory of a very complex collection of possible states, much more complex than you're likely to get in some piece of equipment. It's also true that someday human beings are going to be operating equipment built on this principle, and eventually we need to figure out how that's going to be done. What we did, though, since we needed this continuous supply of possible states, was to make this experiment attractive. It looks nice. It's visually very pretty. And people are interested in it. And when people come up and want to do the experiment, we sign them up. An experiment run starts like this. We began by using the programmer's keyboard to start the system, to run a test, to open a file, and we assign 3 letters as a file name. The person is seated in the experimental enclosure. We wanted to add collections of possible states sort of one at a time and not crowd-wise. So we do them one at a time. The person seated in the enclosure. After the file is opened, the manual toggle is flipped, which makes the operator's keyboard live. Instructions by then are beginning to come up on the monitor. The person reads the instructions and presses appropriate keys on the operator's keyboard. What did we tell people about this? We told them that it was the world's most complicated way to light a light bulb. These lights out here are really very colorful. They're aircraft landing lights, 1,000 watts apiece. We dyed them different colors. And we wanted to see those lights go off. Now, I'm going into some detail about this because it's going to matter a little later. Our objective was to collect 50 trials each time we ran. We've run on 3 occasions, and we've collected by now about 150 trials. I had assumed that the possibilities of the system not working, that is, not getting propagation, were linearly additive, whereas the possibilities of getting propagation were geometrically additive. Based on this, I had initially estimated that we'd start getting results around trial number 50. I hoped it would be sooner, but that was my initial guess. Now, one more thing. I want to be really clear about what happens when someone presses one of these keys. When the person presses the key, that information goes to computer number 3 up here. Computer number 3 tells computer number 2 that someone has pressed a button. Computer number 2 then samples the array. That's the only time computer number 2 will sample the array. That information, computer number 2 decides whether an array event has occurred and sends the information back along the modem to computer number 3. Computer number 3 compares the array event information with the button press information. If they match, the operator is rewarded with lights and bells. Great big flashing lights, bells. We had a siren, but they made us turn it off because it was too noisy. Okay? Now, that's the general scheme of things. And I'm getting to our results, which were outstandingly strange. First, I'll tell you what happened, and then I'll tell you what my conclusions are and why I think it happened. There have been a number of events, but I only have time to talk about the one event that, after analysis, I thought was really the most noteworthy. We ran on a Saturday in September 1988, and during the night, computer number 2 crashed. We don't know why. That's very rare, but there's nothing. We have no idea why that occurred. When my associate came in North Carolina early in the morning, he rebooted computer number 2, which means that at that moment he looked at the clocks, the computer clocks of computer number 1, computer number 2, checked the status of the system, and everything was fine. We proceeded to run through Sunday, and shortly before noon, we came to the end of our waiting list. And we had had a long waiting list continually because people liked the experiment and they lined up for long times to do it. So when we came to the end of the list, we needed to attract some new participants. This was a craft fair, and there were lots of people milling around. I authorized my programmer to blink one of the big reward lights, the 1,000-watt lights, to attract some new people. Now, this is in a gray area of the protocol because those lights are only supposed to be blinked when someone gets an array event. But it was late, it's strenuous to run this experiment, and I didn't have any voice left. And I thought, well, we can always, I'll let him blink the white light, and we can always drop that one out of the sequence later on and preserve our dedication conditions. And I was worried about those dedication conditions because I didn't think my programmer understood them. So I watched what he did very carefully. He took the programmer's keyboard, went through the steps to exit from the experimental program, and called a test program that allows you to blink the light manually. You press a button and the selected light blinks. The test program doesn't use a modem connection. The modem is shut off during that program. Now, he worked on this and he pressed the button. My recollection is that the light blinked a few times. His recollection is that it didn't. What we both agree on is that after he had pressed the button several times, the computer began beeping. This shouldn't happen. And he asked me to step into the enclosure, into the booth, and see what was happening on the monitor. We only have one monitor, so it was in there where the participants could see their instructions. I did that, and I noticed that the monitor was displaying the first experiment instruction screen. Now, to say this was non-standard hardly covers it. Superficially, it appeared that the computer had taken the initiative to exit from the test program, had entered some code of its own to call the experiment program, had entered a set of initials of its own choosing to open a file, and was in the process of dialing ROS. And the programmer attempted to interrupt the program. He didn't like the system behavior, and his immediate impulse was to stop it right away. And he did everything, including finally attempting to warm boot the system. Made no difference whatsoever. He then leaped up, ran over, and threw the main power switch to the computer. If I'd been thinking a little faster, I would have stopped him. But he threw the main power switch, and this stopped the event. He then sat there clutching his keyboard and saying, "You don't understand. This can't happen. This can't happen." Okay. Now, what we didn't know at the time was that outstandingly strange events had happened in North Carolina at approximately the same time. Now, our records show that the last file before this event in California occurred had the file name ABS. The file following ABS ought to be ABT, and our records show that we sent one. However, Ross has no ABT file. In its place, he has a legal file name, but not one we had used on Sunday. It's a completed run with an array event, a sizable array event that passed artifact rejection, recorded, just one event recorded near the end of the run. I would have guessed that is an unlikely place for a solo event, but anyway, we have this one large array event at the end of this run. The difficulty is that that run shouldn't be there. It should have been an early termination because my programmer threw the power switch. There was no one in the experimental enclosure. All right. As it happened, the array event was noticed only by computer number 1, which does continual monitoring of the array. Well, that's reasonable because there was no human being in here to push a button. And computer number 2 will only poll the array on the event of a button press. We wanted as much to ride on the operator's decision as possible, you see. So we can understand why computer number 2 didn't see it. What we don't understand is why, almost 22 minutes later, we had another sizable array event on the same sensor element, which was perceived only by computer number 2. Computer number 1, doing the continuous monitoring, of the array saw no event at that time. Now, looking at all this, the more we looked at it, the stranger it got. And I came extremely close to doing what I've criticized other experimenters for doing, pitching out the interesting data because you don't know what happened. But I wanted to find the bug. And we spent almost 4 months carefully reviewing the entire situation. We looked at the programming, we checked all of our conditions, we checked to see how computer number 1 could possibly have missed seeing an array event. We checked to see just how the extra code could have gotten into the system. We reviewed everything. And at the close of the review, things looked even much stranger than they had at the beginning, and I fully understood why my programmer was so distressed. The systems really are independent. There's absolutely no way that any kind of transaction occurring in the California end of the experiment can possibly cause an array event by any mechanical or electrical or electromagnetic means. As far as we can tell, there is absolutely no way the computer could have gotten hold of of the code because it was not in the buffer. There are multiple reasons that it could not have been in the keyboard buffers. I could go into much more detail on this, but we spent 4 months on it, and I can't cover the entire issue. I can just tell you that we checked very thoroughly, and I began to make a list of all the coincidences, geomagnetic surges, whatnot, that had to happen to account for this event, and the list was too long. I finally realized that yes, this is a propagation event. It appears to be a propagation event of exactly the type described in the theory. It's not the neat Newtonian form of propagation we'd hoped to see. No one during this experiment so far has managed to push a button and turn on one of the big lights. The other hand, we've seen an array event with a remarkably large time-wise anomaly. I had expected the generation of time-wise anomalies in this system, but I thought they would be small, 2 seconds or less, which is undetectable in our current scenario. We didn't have specific equipment to look for it, and I was just going to ignore it. And a separation of almost 22 minutes says that there is really an enormous quantity of effect that's actually banked in the system. It's banked in there by the control of possible states. In other words, it appears that the strategy of stocking the system with possible states by simply adding operators, this strategy worked. Could the operators push buttons and control the system? No, not yet. But we certainly could, because this event happened essentially as an infringement on the dedication conditions. I had thought it was a gray area, but apparently it was not. Because I think what happened is that the system, the dedication conditions, had established the system protocol as a powerful state, a powerful resonant state. And I think it spontaneously made transit to that state when the programmer attempted to violate those conditions. Now, a state-separable system, a system built after this theory, should be able to do that. Now, just what happened with our array events. One more detail, and then I'll leave it open to questions. Earlier, the part of the theory that went by quickly, but that I insisted you see, had to do with the propagation of effect between resonant matrices. Matrices that are resonant and have the same relevant dimensionality, you might say they respond to the same event generation transformations, share certain characteristics. What happens in one tends to happen in the other. These two computers were symmetrically connected into the array. I think they were images of each other. I think we had not 2 array events, but 1. And I think that array event split between the 2 computers. And I think the size of the split was almost 22 minutes. We divided an event in this experiment. All right, I think that's I think that's as far as I can go in describing what happened and what I thought about it. I'd like to have your questions now. Yes?
I don't understand the sequence. The operator hits a key on the keyboard. Now what happens from there?
The operator hits the key on the operator's keyboard. Computer number 3, that key press goes to computer number 3, which is in California. Computer number 3 notifies computer number 2 in North Carolina that a button has been pressed. Computer number 2 checks the array for events, goes through artifact rejection procedures, and sends the information, events, no events, on each of the channels, back to computer number 3. Computer number 3 checks to see what button the person actually pressed. If there is a match, computer number 3 activates the control box to ring bells and flashlights. Yes?
The important question, what is the criteria of match? Can you tell us? How would you say two events match?
You mean with regard to the...
What is your matching criteria?
All right. If you're pressing a green button, you expect to get the green light. That's associated in the system with a particular array element. So you press the green button. Computer number 3 sends that information to number 2, which checks the array. The information comes back to computer number 3. If you have a hit on green, the green light goes off. You get flashes of the green light in the light display out here.
Wait a minute, you have some events up there,
Yes,
and you have an operator down there.
that's right.
Okay, how do you associate a certain button with a certain event up there?
In the
What is
theory,
green up there? I understand what you're
okay,
down.
there's a collection of lights down here, different
Or
colors.
clear.
There's a program which associates the color of those lights with a button press on the operator's keyboard. You want the green light, you press the green button. Okay.
Now,
There are 4 detectors in the array, and each detector is currently assigned to a particular color. That's not an optimal way to do it, but we only had 4 elements. We only had 4 array
you have
elements.
reassigned a certain event to a certain color in
Well,
Carolina.
yes and no. We have 7 big colored lights, so some of the buttons do double duty. We'd like to have a much bigger array and a more complex system, but this is all we could afford for now. Yes.
I'd like to know what is the relationship of the experimenter's decision to press the button, which occurs before the button is pressed, to the experiment as a whole.
Well, we'd all like to know that, and if we had more events associated with operators rather than the system itself, we could tell you. But we knew that we had no idea how that variable would work out, or whether it's a person's decision to press the button that does it, or, we really had no idea. We had no precedent. So what we do is during a button press, suppose, in North Carolina they keep a continuing history of the array activity, so that when you press a button, let's say you press the red button, that information goes to North Carolina, and we take the information from 3 seconds in the past on the red button and 3 seconds into the future. During that 6-second interval, the computer doesn't recognize any other colored button presses by you, and during that interval, if you get an array event on red, you're going to get the red light and major congratulations from the system. Yes?
So I have two questions to ask. One is practical. How did you test the noise in this system? How reliable is your system? What kind of level of noise you have noticed here?
Well, the noise here would be principally noticed. I think you're asking how much artifact we have, how many artifactual array events. And the answer is very few. Very few. During the normal baseline, in a 2-day period, running steadily for an entire weekend, we might have 24 of them. It's not a great many. It's more than I would like to have, but it's a fairly rare event.
But is it some type of a controlled experiment that you expect, let's say 3 and you get 3, or 0 and you get 0? Can you control your equipment there? Because that's how, let's say, I would do experiment.
Well, this experiment is based on the control issue, the on-off switch problem. And the whole experiment amounts to a giant toggle switch. We're trying to make a switch, in effect, not a little black box that we can, that we can sell, okay? We're trying to make a switch, a control system, which will turn on the event generation process, which will initiate that process. And to do that, we stopped the system with effect, with possible states as well as we could, and we attempted to control the possible states of the components through dedication conditions. Later on, we'll be able to do much more refined work. Since the system apparently did, the indication is that the system did make transit to a powerful state. It did perform as we wished, although not as we intellectually thought it would. Later on, we should be able to get much more exact system performance.
The other question was, do you need all those drastic assumptions in your theory, like you mentioned, of instantaneous interaction and all those, which we know what that means in physics? Superluminar, all kind of stuff you were talking in the theory.
Yes.
You need all those things?
Yes. The theoretical universe needs to be able to contain everything that can possibly happen. And yes, that's the essence of the theory. All that is in there. Okay.
What would you entertain the addition of an identical force detector array as a control that was under continuous monitoring as well?
Well, the issue of control is a very strange one in this system, and I hope someone would bring it up in this context. Effect propagates between images. An image, two objects are images if their possible states are sufficiently similar. We can produce a mathematical criterion for this. Control propagates instantly between images. Since that's so, if you were to set up in a controlled experiment, the theory doesn't say that you can't do controlled experiments. The theory does not say that you can't take an experiment and then do an almost identical experiment. What the theory says is that the two experiments are not independent, that the results in one are going to affect the results in the other because their possible states are resonant, and effect is going to transit. And I can think right away, I'll give you one example where this happens, this notoriously happens, and that's in medical studies. Think about medical studies where they're studying drugs. They have a group of people given the drug and then tested elaborately to see what happens to them, to see if they get better. They have a control group of people treated in exactly the same way, very strictly the same way, who get an inert substitute, the placebo. Oddly enough, the placebo is one of the more powerful effects in medicine, and it even has side effects. Now, why does the placebo effect happen? If it isn't the reason explained in this theory, I really don't know, but it certainly is a powerful effect in the literature. Thousands of studies support it. I think we should close now.
Yeah, we have to. So.
Okay. Thank you.